Hey,
Yep. But here's what we're going to do. I'm going to do two quick things. One, I'm going to introduce Emma to PJ because PJ is with us today. And then I'll introduce PJ to Emma as well. But PJ, thank you for being here. This is the Eli Madison Memorial Apprenticeship Foundation. We're putting together an apprenticeship program. And we're going to start taking men and women who have a desire to be in the IBM space, and we're going to put them through IBM apprenticeships with the use of, we have Dr. Cameron Say, if you know the name, and
yep,
we have Professor Jeffrey Decker, if you know the name, from
yep.
Northern Illinois. And so both of those gentlemen decided to come together with their tenure of collegiate COBOL, IBM, assembler, mainframe, everything space. And we built a team here at Emma to bring the men and women out there that want to be a part of it. And we're going to put them into careers. And so that's what we've done. About 45 days ago, PJ, this didn't exist. Cameron made a
Awesome.
post on LinkedIn. About 2 days later, a couple of us got together with Cam, and we decided to come together and put this forward. And now, just a couple hours ago, you guys, we have a official logo. We're going to start to put out there.
No
We have a
way.
website that's about to come out. We've got some really big things happening, and we've got a lot of people coming in every week to hear about our progress and hear about what we deliver for them to get into their careers, starting with IBM. And so,
Great.
PJ, thank you for being here. Thank you for being our inaugural guest speaker. And to everybody on call, if you don't know, PJ Catalano, the one and only, he's coming to us via what I'm going to say is LinkedIn, because that is where I know PJ from. PJ is a huge influencer. I'm going to use that term, PJ. I
I
don't know if
love
that
it.
is
I love it. I
a
love it.
space. Listen, if you want a meme Monday, or if you want to know what the next most TikTok trend is for IBMers, this is your guy. And not only that, PJ has a huge influence into the next generation. When I say next generation, you, the men and women on this call, are the next generation of IBMers. And PJ is not only a huge influencer of that, he's a huge advocate and supporter of that next generation. And so I'm honored to introduce PJ. PJ, again, thank you for being here. PJ this evening is going to give us a tour, excuse me, a virtual tour, but a virtual tour of not only what he does, where he's at, and what he provides, but y'all are going to get to see some very, very cool inside stuff in the IBM space. PJ, the floor is yours, sir. Thank you.
Awesome. Awesome. Cable, thank you for that amazing introduction. It's a pleasure to be here, an honor. If you don't know,
PJ, I just muted you, PJ. I hit the wrong button.
okay, I'm back. I'm back. So,
That's my bad.
if like I said, if you don't know me or don't follow me, I'm hoping by the end of this talk, this tour, you get a sense of who I am and why I'm so passionate about this awesome technology. I am going to share here while I'm talking, and we're just gonna go and jump in. Let me see. Can I make this bigger? We'll do our best here. Okay, so hopefully you could see my screen here. So this is the insider's tour of the IBM Z Linux One test facility. I am the IBM Z Linux One and test architect. This is a little bit about me and who I am. I'm not, this is an eye chart, but this gives you a background of over each of these boxes represents about a year of a career summarized in one sentence is to kind of highlight, which is very hard to do. Up until about this purple box, the rest kind of is recent history here. I've been IBM at 20 years. I started in college as a co-op, and it stuck. I loved it, and I never wanted to leave. Not only am I the test architect, I am also a senior technical staff member, which is an appointed role at IBM, and the master inventor at IBM. And I'd love to talk about inventions and inventing, but that is a different talk. And if you want to invite me back for that one, we'll do that one too, because I
Okay.
love talking to people about all the cool stuff. But let's get started. So hopefully you can see me here, nice and big. I am going to warn you, I see myself mirrored in this thing. So I'm going to point to things and I'll be pointing in the wrong direction all the time.
Okay.
I have my little pointer cursor here. I'll try to remember to use that versus point. But if you see me pointing off into space like that, I'm just so excited. I can't help myself.
That's
So
perfect.
we're about to go see our test floor here. This is a 80,000 square foot facility, about 7,500 square meters. If you like freedom units, if you don't like freedom units, and we are on a 30-inch raised floor. Okay, so you can see If I find my mouse here. I don't know why this is freaking out. I do apologize, but we're about 30 inches off the ground here. And that's because all of that is how the cooling happens in a data center, and we're going to get that fixed. So my network performance is a little crazy here. Give me a second to try to see if I could fix this.
I did the same thing. I kicked the kids off and told them they can't game for
yeah.
75
My son's
minutes.
probably playing Space Marines 2 in the basement. That's fine. Or Fortnite. So let's go inside. It's going to be loud. It's about 80 decibels. Now, it's not really loud. If you were in person, 80 decibels is about the sound of a vacuum cleaner running. So hearing protection is required if you're on there for an extended period of time. There is no audio, just my voice, because I love hearing myself talk. But we're going to go see what it takes to kind of test the world's most reliable platform, which is IBM Z and Linux One. So let's head on in, and we're going to walk and talk.
Yep.
Maybe. Maybe. Okay. I got to click on the thing there. Okay. So we're heading into the test floor here. The first thing you notice that, we have 200 mainframes in Poughkeepsie, New York. So I should have mentioned, this site is located in Poughkeepsie, New York. If you're not familiar with Poughkeepsie, New York, we are about an hour and a half north of New York City along the Hudson River. And this is what a data center looks like. Now, if you're actually here in person, one, as I mentioned, it'd be really loud. Two, if you look down the hallway all the way back here and looked at the lights, you'd actually see the lights twinkling. It's not because we have special effects, but these things generate so much heat. And my density per square foot is we are the world's most dense MIPS per square foot data center in the world. Generates a lot of heat, and all that heat rising kind of makes the lights twinkle.
Wow.
If you're not familiar with data center layout, we do have a hot cold aisle configuration. Okay. And what that means is if you look on the floor, you're going to see some aisles down this way that have kind of these floor grates on them, which are holes. Yep. And then the next aisle is going to be solid, no. And then the next one's going to have floor grates. Why do we do this? Well, in a data center, machines need to be cooled and generate a lot of heat. If I have systems that are facing in the same direction, row after row after row, the first guy is going to get cold air, heat it up, and then blow hot air out, going the wrong way, into the next guy. And the next guy is going to get warm air. And as I get down the row, my air is going to get hotter and hotter and hotter. The systems down the rows are going to get hotter and hotter and hotter. And systems don't like hot air. We want to cool them to keep them highly performing. So we rotate them 180 degrees every other row. This forces a convection current. So cold air comes up from under the floor. They rise up through these grates and then gets sucked into the system. So this system's heating up the air, sucking it and pushing it back through. And then hot to hot, the hot air blows to each other and then rises up to the ceiling. The hot air causes all those lights to twinkle because it's warm. And if you look down the aisle, but then this big unit behind my head here, this guy over here, this is called a CRAC unit, a computer room air conditioner. And this guy's job is to suck the hot air off the ceiling, chill it, and then blow cold air under the raised floor and creates this convection loop, this forced convection loop.
Okay.
And that is a hot aisle, cold aisle configuration. Okay. By the way, I can't see the chat. I want people, if you have questions, just yell out, talk, ask, please. The more interactive this is, the better it is for everyone. So, yeah, I wanted to mention that.
PJ, I appreciate that. So to me, your analogy, the heat, is that like when you're driving down the country road or the desert road and you see the heat come off the road?
It's the same process. And that word actually has a name. That terminology of seeing that kind of wavy light is called scintillation. Okay. So what that means is the light warping as it's moving through hot rising air, it warps. Okay. So it is the same process. Usually you'll see the heat rising off the road fastest. So that's why it looks like water on the road. But here, most of the heat lives on the ceiling, right? So it is the same physical process called scintillation.
Okay. Thanks,
Great question. So we're going to swing around here and we're going to start taking a little deeper look into the hardware. I want to show you some components up close, talk about what we do and how we test some of them. And then we're kind of going to go build up and look at the infrastructure and kind of the overall system and how it comes together. So we're just walking down here. And I first wanted to show you this little guy that we're about to come up. Now, all of our systems have a designation. Usually it's a letter and a number that we call it. But this guy actually has a name. And this guy's name is Beamer. Okay. Why do we call him Beamer? Well, this special system we actually load in a van and ship it to a medical university in Boston. And we fire every single hardware component in this box with the proton beam. Now, what is a proton beam? Well, it's the same laser technology, radiation technology that's used to treat cancer patients, right? So after chemo, radiation treatment, we take that laser, we put this guy in a chair that a cancer patient would be in that's undergoing treatment and fire it at every single hardware component. Now, why the heck would I do that? Well,
Yeah.
Cosmic radiation, right, actually interferes with electronic equipment. Okay. So the gamma rays that are coming in when they hit electronics can actually cause bits to flip. Zero become ones, ones become zero. Now, I'm a test guy. I can't plan for the sun to emit a cosmic ray and line up my thing perfectly here. So I need a way to simulate that process in a measurable time frame and control, right? So that proton beam actually causes that same gamma radiation interaction with the electronics to cause bit flips. So if I was my bank account, right, and accidentally one flipped to a zero, usually it probably wouldn't be in my favor. I'd be really upset, right? If your bank account was sitting and undergoing a transaction and because of some solar flare, the accounting was wrong, that'd be horrible, right? So we actually built into our design a test that allows us to predict the incoming solar radiation and then make sure our designs are hardened enough to detect errors that are caused by this, right? So we've actually taken cards we've built, hardware we've designed, and actually thrown them out because they failed this test. Now, there's some types of hardware that are more susceptible to this radiation than others. For example, FPGAs, field programmable gate arrays. If you're an electronics person, right, these are programmable logic type of chips are very susceptible to this radiation incident. So we've had cards designed with this type of FPGA built in that we actually had to throw out and say, go back to the drawing board. They're not hardened enough. We cannot detect all the errors at the correct rate that we expect, which could basically cause some data integrity issue, right? Yep. Which is our #1 job to prevent that from happening on IBM Z and Linux 1. So Beamer gets shipped around to medical universities and gets fired with proton beams around the world.
That's wild that you guys are actually taking, and I would say faking, but replicating the solar flare or the emissions that are coming in to test your units to make sure that they are susceptible or not susceptible to that stuff happening.
And we take this very serious, right? You know, you think of this as like an esoteric case, a corner case. Like, why would anybody ever think of that? But you have to remember, IBM Z is running some of the world's most important data, right? It's financials, it's governments, it's banks, it's insurance, right? The types of data that if you had an accidental bit flip would cause some real issues, right? So we need to account for any condition, right, that could cause that and make sure our designs are really tolerant and be able to either recover from them or at least detect that it happened, right, to kind of stop transactions that continue to flow. And that's all part of our design effort. It's not an afterthought, right? It's part of the built-in design and test process we go through every generation of system here.
So do me a favor, there's a question in the chat from Oscar. What are some of the most surprising findings from this type of radiation testing on your mainframe equipment? What's some of the most surprising things you found?
Yeah, so like I said, we've had some cards where IO cards where so we do encryption on the IO. The first early implementations, we were planning to do the encryption via an FPGA, right? Where we could kind of take this logic and then reconfigure it to do different types of encryption algorithms on data in flight. We found that the FPGA, like I said, is not hardened enough, right? Where we actually had to throw out the whole encryption FPGA and replace it with a hardened ASIC. An ASIC is kind of actually like built into metal on silica. It's not programmable. You build it once and set it. So, you know, that's kind of one of the most recent things in recent history that I can remember where we actually had to throw out a whole IO card design and say, start from scratch. So those are the types of things we're looking for. And yes, we will scrap whole designs if it doesn't hold up to that. Right now, We knew there was a chance. We thought the tolerance from the vendor of the ASIC that of the FPGA we bought would be able to handle it, but we proved it didn't.
I love it because PJ, not to interrupt you, I apologize, but
No,
earlier
no,
in our
please.
chat, we were talking about a niched community, and one thing I want to talk to everybody on the call about is, again, proactive versus reactive. Not every company out there are taking those measures to take that precaution and even understand that that's a precaution. I mean, I'm sure they do.
Yeah.
Whereas IBM built it in, and it's a standard procedure that they do from the beginning. That's awesome. Thank you.
Yeah.
Thank you, PJ.
Oh, you're welcome. You're welcome. And keep the questions coming, please. Cable, thanks for reading those out.
Yeah.
So we're going to swing around here, and we're actually going to take a deep look into the Keck drawer. So when you look at Z in Linux 1, right, they're kind of some modular building blocks that we kind of reconfigure in different configurations. What we're looking at is the Keck drawer, or the compute drawer, right? So this is where your processor and RAM, main memory, live, right? So this whole unit here is the Keck drawer. Now, what you're looking at, let me start down here in this corner here. So this is what we call a DCM, a dual chip module. IBM's for Z16, Telum was the name of the processor. So there's two Telum processors in a dual chip module. Very fancy name. Would come up very creative. Dual chip because it has two Telums. We recently just announced Telum 2 for the Z Next, which will be the next generation of mainframe at Hot Chips a couple of weeks ago. But this is the Telum 1 we're actually looking at here in this module. So in this module, right, there are 44 billion transistors.
Wow.
20 miles of copper cable, okay, in each of these, right? So, and in every Keck drawer, you get 4 Telum processors. If you look at this kind of hole here, these are the sockets the DCM sit in. So you get 4 sockets in every drawer, and everyone has 2 Telum processors. Every Telum processor has 8 cores. So you get 32 compute cores per drawer.
And you've got them just laying around the office, right? Just some Telum chips.
We have hundreds of these, and I'm going to show you that, right? But yeah, it's fun to get your hands on these things.
Now, I need 2 of those right now in South Texas.
Come and get them. Come to Poughkeepsie.
Yep.
Get you some. So what we're actually looking at here is kind of there's 2-ish versions of the mainframe. There's the high end, and then there's the air-cooled system. This is a high-end system, and we know it's a high-end because you can see these black tubes here. These black tubes are connected to these copper cooling plates, and those cooling plates connect directly to the top of the cap, right? So this is actually, so this guy down here has the lid cut away, so you can see the Telum processors. But if you look at the guy down here, right, this is what the full lid looks like, cap, and then you connect the cool plate to the top of that. So this is a high end. It has a water cooling loop. That's what the black tubes are. We'll see what the full reservoir system looks like at the system. If you were on an air-cooled system, instead of these cooling loops, you'd have this big giant heatsink above my head. This big hunk of metal on each of those DCMs. Now, why can we use that on the air-cooled? Well, the processors run at a slightly slower frequency. They generate less heat, so the air cooling can keep up versus the water cooling. Okay. So 2 different kind of models. There's different variations within the models there. But that's kind of the 2 big main differences. If you look to the left here, you're actually looking at the RAM. So these are custom RAM that IBM builds. In each drawer on Z16, you could have up to 10 terabytes of main memory, 10 terabytes of RAM. You could have up to 4 drawers, 40 terabytes of RAM, basically in a Z16. In Linux 1, we actually let you go up to 48 terabytes. There's limited I/O configurations, but you could go up to 48 terabytes of RAM in a full configured Linux 1 system. Okay.
PJ, do you want to hear about my first compact computer I bought from Radio Shack and how much RAM it had on it? No, I'm kidding.
No.
Go ahead.
And then in between, there's other components. Now, the hardest test we do is get the full system up and running, inject an error on, we have tools that allow us to physically inject errors on either the memory or the CPUs, have the system recognize the fault, and then replace and repair the unit without having to shut down any of the workload, right? The system will keep running, and we can replace every single component in this drawer while the system is running. You need at least 2 drawers to do that, but if you have 2 or more drawers, fully repairable, fully redundant without having to take any hit to your workload. The system will keep up, going, running. We'll do a verify, plug it back in. The system will do a checkout and then redistribute the workload across all the available drawers.
That raises the question, hot aisle, cold aisle. How is that possible?
How is it possible? Well, so the systems aren't back to back, right? There's gap between each system. So we'll take a look at a drawer on the cold aisle side. The drawer actually pulls out into the cold aisle. Okay.
Yeah.
So it's on rails. You do the replace of the components and then you slide it back in.
Without getting shit shocked out of you because it's 3-phase.
100%. So one of the main things we do is, now again, it's an IBM service person that's going to do it, so they're trained how to do it. Second is we do a lot of safety testing as well.
Come on,
we ensure that
we can all do it.
All right, we'll figure it out, I'm sure, eventually. But yeah, I mean, it's a big system that costs a lot of money. You probably want somebody who knows what they're doing to touch it. But yeah, it's all repairable. We do all safety systems. We actually have like a fake finger. It's a metal conductive finger where we actually try to jam it into basically every hole to make sure we can't measure any voltage, right? So you can't shock yourself. And basically anywhere you see a hole, we take this metal finger and try to jam. That's part of our testing. We also have another rubber finger too that we do the same thing for, like fan enclosures or things that we think people could get their fingers jammed in, to make sure you can't do that, right? So a whole set of compliance safety testing that goes into making sure that our service personnel that install and repair these things are never in harm's way, right? So that's a big effort as well.
PJ, awesome. Are you guys still doing the paint shaker test?
You mean to check the color?
No, the vibration tests.
The shit. Gotcha. So we actually did a test where we were testing the colors of the powder coated doors. I thought that's what you're talking about. But so we do shock and vibe testing. We do a test where we have to ship these things around the world. And one of the most kind of vibration happens is when these things are loaded into their cargo containers and then shipped on an 18-wheeler, and then expected to arrive in one piece, because we build and manufacture the whole thing in the frame, right? And then we ship the customer the thing already configured in the frame or sets of frames. So we take it and we actually will load the fully loaded system in the shipping container on a shake table, and basically do a simulated 18-wheeler going down a highway at 60 miles an hour, right? And then basically open it up, make sure all the brackets stay. That's one sort of shake test we do. The second shake test we do is operational vibration. So we'll get the system up and running, workload, operating system, and then basically simulate like a freight train that's real close to your data center ripping through. So it's a lower frequency than like shipping on an 18-wheeler, and make sure that everything keeps up and running. And then we also do an earthquake test, right? Where we actually will do a simulate. We don't do that in Poughkeepsie. We do that in a university in Reno, Nevada, where we will simulate a Richter 8 earthquake with the system strapped. And that test is not to ensure the system operates through that. That test is to ensure using so we have an extra earthquake harness, right? So if you're in an earthquake prone zone, you would get this harness so the system doesn't tilt, right, and hurt somebody. So that's the scope of the earthquake test. People think like, oh, the whole thing's going to work through an earthquake. It has, and we have evidence that it does, but the earthquake test is really to ensure, the system doesn't fly apart, the thing doesn't tilt and fall onto somebody, right? If you use these rigid strap in the frame stiffeners, right, that components aren't flying out. Safety is the goal of the earthquake test.
Very cool.
Yeah. Boy. So behind me are my giant air fryers. So I have 4 of these thermal chambers. These are these big boxes, and each of these I put a system, get it up and running, and then I swing the outside air temperature from 5 degrees Celsius up to 40 degrees Celsius. In freedom units, that's about 50 degrees C to 110 degrees, Fahrenheit to 110 degrees Fahrenheit. That's the operating envelope of IBM Z16 and Linux 1. We then also change the humidity and then change the voltage. We're basically simulating different types of altitudes, right? So as you get higher in altitude, it gets harder to cool. We want to make sure we have a big enough range that if somebody wants to put a mainframe in data center in Tibet, you could cool it. And by the way, they will work 3,000 meters above sea level at maintain cooling.
Wow.
So if you want to try it, you can. There's no data centers in Tibet yet, but maybe one day there will be. So that's what we do in these thermal chambers.
Very cool.
So we're going to walk all the way to the other side of the floor and start looking at some of the I/O. When I started, IBM, the first thing I did was a vendor testing. So we have the vendor solution connectivity lab, third-party hardware networking equipment, right? So things like switches, SAN switches, storage area network switches, and some of the telecom equipment, which I'm going to show you a cable you might like this coming up, is DWDM, right? So dense wavelength division multiplexers. So my first job was to actually test this thing right here. So this is a DWDM, as I mentioned, dense wavelength division multiplexer. Yep. And what you notice is how this is pretty cool technology. If you look at all these cables you'll see are mostly yellow. We're going to look at some more cables later. But all the light, right? All the fiber optic signal running over over these yellow cables are the same color. They're 1310 nanometers. That's the wavelength of the light. But for this, they're all the same color, right? What this system allows you to do is take each of those cables and then convert the light to 160 different colors. You say, why the heck would I want to do that? Well, light's non-destructive. So I could take 160 different colors, stick it through a prism, and put 160 different colors, 160 different IOs, basically channel signals over the single piece of glass here. Okay. Yep. So why would I want to do that? Well, if I have multiple data centers, right? So for a disaster recovery, I have my primary data center and a backup data center. To run a big sysplex, a real big Z configuration, it could be hundreds of fiber optics connections to keep that thing up and running. Well, running hundreds of fiber optic connections, say 30, 40, 50 kilometers or miles, like that gets expensive really fast. But if I could take 160 signals and just run one cable or two for redundancy, 50 kilometers, I could get a lot more bandwidth out of that. So that's exactly what this allows you to do. If you look at this silver box up top, this cable's running into, that's 50 kilometers of real fiber optic cable. In the frame next to him, I'm pointing the wrong way. In the frame next to him, I warned you, there's another 50 kilometer box here. So this frame that you're looking at is physically 100 kilometers away from the frame right next to him. Okay. Wow. Now it's like, well, what's the point of that? Well, again, for a disaster recovery, right, we need to test multi-site sysplexes. Sysplex is a fancy Z term for basically a Z cluster. And we need to do that at distance, and we need to be able to do the disaster recovery at distance. So I'll take my Z, attach it on this side, and take a storage box and attach it on that side, 100 kilometers of latency to make sure I could do my reads and writes over that distance. And we do this for coupling. We do this for storage traffic, our FICON and fiber channel, as well as all our Ethernet protocols, Rocky, Ethernet, and I think that's really the main ones we extend over this box, right? So WDM, pretty cool technology. This is where I started my career. I love talking about it because it's not stuff many see. Now, these are the staples of the telco, right? This is the backbone, right? So your cell towers that you're connecting to, you're running over some sort of this equipment. It could be Ciena's the big players here, Adva Optical, Cisco, kind of all make DWDM technology. There's lots of smaller places, Alcatel-Lucent. There's what else? I'm missing some Pad Tech, right? Bunch of do this.
Well, when I left telephony, I was at 8. I was on copper, right? Straight copper wires. So I was at 8 channels of signal being able to go down a single line. And the danger of that was, again, voltage and everything going across that was but then when fiber came out and we went to this, we still weren't even at 160. They didn't even go that far with it. It just tripled the amount of signal going across the fiber. And then the speed, of course, at the time was huge versus copper.
Yeah, it's all OC1, sonic kind of containerized and kind of multiplexing. And like you said, you could take multiple slower speed channels and then put it over a bigger pipe on the back end. So I could take 10 gig signals and then have 100 gig lambda wavelength on the back end, right? To kind of really pump those guys. Like these are 402 terabyte, lasers on the back end. So you could kind of aggregate a bunch of lower speed subrate channels, multiplex them, electronically, transmit the signal and demultiplex it electronically, as well as the physical multiplexing of multiple. So you could stack this and kind of get really, really serious bandwidth between multiple sites.
That's awesome, PJ. Thanks.
Oh man, you're welcome. So we're gonna go look, and I mentioned a little bit about storage, right? So we're gonna go look at some of our control units. So control units is the fancy Z term for basically just saying some sort of storage device. What you're seeing behind me are DS8000. DS8000 is IBM's enterprise class storage. Just last week, we announced a brand new, it's the DS8A. I don't know how to say it. We say 8900, 8800. Now there's letters. So DS800, I don't know. So these are the kind of N-1 now and N-2, right? 8900 was the latest and greatest up until a week ago, and then 8800. So what we do is we talked about disaster recovery. So how disaster recovery works is you basically need 2 copies at a minimum of data, and you really don't want them in the same site, right? Because if you lose that site, you lose all your data, even though you had 2 copies. You want to take those 2 copies of data and keep them separate, right? So that way, if you have a disaster in one location, your data is still good in another location. To keep them in sync, it's called disk replication technology. So there's 2 forms, synchronous and asynchronous. So synchronous, you could think of, hey, I deposit $100 here. My bank account gets updated here, but I don't acknowledge that, it's active until I make a copy from this guy to this guy. And then I tell that guy I made the copy, and now he says, okay, go. So that's synchronous. Every action has to have a replication before we say, yes, the work's done. Asynchronous is I do the work, I do the work, I do the work, and then at 5-minute intervals, I'll then do a copy over, right? Well, why would we want to do that? Well, the distance as it grows between those synchronous replication, you're adding more and more basically back and forth latency that at some point your application may not tolerate that. So you have to go to an asynchronous mode. Now, in that asynchronous mode, you could have, some data, I would say inconsistency, not data loss, because we could regenerate that data. We do have a ways to do that, but there's a period of gap that you got to go do extra work to kind of get that data back. So multiple forms of disk copying. So what we'll do is, as I mentioned, we'll take this guy, plug him on one side of the DWM, take this guy, plug him on the other, and I'll do writes from my Z to this guy, the local guy, and he's replicating the 100 kilometers. And then at some point, I pull the plug on this guy and make sure I can read all my data back from that guy, right? 100 kilometers away. The Z goes 100 kilometers out over the DWM to attach him, just like a real customer would, and make sure I can read all my data consistency back. And we're doing this, across multiple sets of control units, right? In multiple different configurations and multiple types of sites, right? As well. So that's kind of how we do a lot of our disaster recovery testing on the same site without having to build another data center like New Jersey and run really far or drive really far to see if my data consistency is correct. I could do it all here in one building.
So you're looking at the 100 kilometers, but is this like in my brain goes here? Is it like a timestamp where you're going to stamp it off and then check it all and then continue from that point? Is that what you're saying?
So that would be a asynchronous example, right?
Okay.
So
okay.
The synchronous example is you walk up to an ATM machine and say, give me $100, right? The ATM machine will not give you $100 in the synchronous until both copies say, I've deducted $100, and then I'll give you the $100.
Gotcha.
In asynchronous, only one copy has to say, okay, the $100 is deducted. And then at some other time, I say, yes, copy it, but then we do the timestamp verification to make sure we're in sync over time.
Okay. All right. I appreciate that.
Yeah, you're welcome. You're welcome.
Good analogy.
PJ, do you know if companies like ComDisco are staying, shall we say, current with the hardware, or are they still behind times?
I don't know.
Okay. The reason I ask is I worked for a bank.
Yep.
ComDisco Chicago, the burbs, was our hot site. Ohio, Bank One in Ohio was our check processing site, and we had to do, long before there was fiber, connectivity. I just was wondering if they were keeping straight, because we did everything tape backup. Go to ComDisco, restore, start over.
So tape is having a resurgence, by the way, if you've been following the industry. IBM about a year ago, IBM Research announced a 50 terabyte tape cartridge.
Wow.
So what happened was a lot of people were basically saying, I'm getting rid of my tape. It's too slow. I'm going to back up all my data to the cloud. The prices of cloud started going up. Companies went, this is too expensive. I want to back up my data to
Yep.
tape again. So we announced the Diamondback, which is like a 9 tape drive robotic arm thing. Go check that thing out. Go Google Diamondback, IBM Diamondback. It's this massive tape containment and loading. It's amazing. So tape is actually coming back in the industry. The other problem is a lot of government regulations, because these industries we work in and operate in are very regulated industries. Like I said, it's some of the world's most important data. It's got to be regulated. So the location of data, which countries the data can reside in, needs to be tightly controlled. And if you're putting your stuff out on the cloud, you're at the mercy of the cloud provider, right? But if it's in your data and warehouse and you know where that tape is, you can control that to make sure you're within compliance, right? So it's another reason why tape is making another kind of resurgence here in the post-cloud era, which I think is just hysterical. But I love it. So we actually still have tape drives in here. I don't have it in this presentation, but we still do some tape backup. Again, customers are using them. We have to test it. So yeah, look for tape. It's coming back big.
I love it. I love it. I mean, I still have all my Disney VHS, right? I mean, I get it.
Yeah. Betamax only. Sorry,
yeah.
VHS doesn't
Yeah.
work.
That's right.
Hey, PJ, this is Cam, and this is can you hear me? Can y'all hear me?
Yeah.
Yeah, thanks again, man. This is great for you to do this. So what y'all were talking about kind of dovetails into something I was discussing with my students today. At one point in time, the ratio of equipment on-prem was thought to be 0. Everything else that you put in the now nobody says that ratio is 0. Something's got to be on-prem. It's just a question of what it is. And so I think that's where we are. Something's got to be on-prem. You got to have physical access to something in your infrastructure that you control completely. Now, to the degree to that, to the extent of that, but it seems to me, correct me if I'm wrong, but it seems like people have come to the conclusion that we got to keep our hands on something. Correct me if I'm wrong.
Yeah, no, you're right, and especially I'm going to say these regulated industries where there's more and more. I'm going to say the governments are getting smarter about data vulnerability and data access. So you'll see things like, hey, bank, prove to me you could run, if you have multiple sites, data centers, prove to me you could run production out of this data center and fail back. That was a regulation, I'm going to say, for 10 years, right? And banks would demonstrate that. There was a new regulation that said, okay, show me you could run at this data center, fail back, and then come back to your primary data center within 48 hours. You know how much pain that actually caused, right? It sounds like, oh, failing in one direction is easy. Failing back is actually very hard, right? So there's lots of you need to actually show evidence, right, that your equipment can hold up to these. And the only way you can do that is by, from an audit point of view, is actually being able to control the flow and where that data actually runs. In an AWS region, you could maybe select the region, but you have no idea where it's running and how do you prove it actually failed back, or if you're just getting an IP address from another machine, right, that's ghosted through something. So on-prem or a mix of hybrid cloud, right? That's the term we use, where it's a mix of on-prem with cloud connectivity and multiple cloud vendors. So you can move your data around to where it makes sense for the application, and also because of cost, is really the future. It's a mix of on-prem cloud connectivity and the data residing based on compliance and regulation and governance, and then also cost, and then giving the customer the ability to decide where the data and the machines live on a whim, right? That's the future of data centers.
Wow. Okay. Hybrid cloud. I put that in the chat because that's an interesting concept.
Yeah, go check it out. Hybrid cloud. There's multiple definitions of hybrid cloud, right? But that's the term we use for kind of our suite of infrastructure products fall under this hybrid cloud strategy as well.
So PJ, I love that. Go ahead, Kim.
Go ahead, Kim.
No, go ahead, Kim.
No, that's what I teach. I don't teach mainframe. Mainframe is part of what I teach, but you cannot have the reason the term hybrid cloud is really important as opposed to cloud. The hybrid cloud term encompasses the mainframe.
It absolutely does.
Yes. There. So I teach hybrid cloud, and I shared this with my team a little bit, and they didn't really get it, and that's okay. They pushed back. I said, "Well, it's a little too esoteric," and I get that. But that is what we do.
That's what we do. That's right.
You can't teach mainframe. You got to teach mainframe in conjunction with all this other stuff. So that's why I use the term hybrid cloud.
Yeah. No, that's absolutely the right term.
No, I appreciate that. And Cam, you're right. A little esoteric for myself, but I'm getting there. I'm getting there. Hey, real quick, PJ, before you go on, there is a question in the speaking here in the chat, but I don't want to derail you. If this does, just let us know and we can come back to it at the end. But the question is, we're talking about the future with rapid advancements, both in AI. Do you see the integration into mainframes, and how do you foresee AI-driven automation transforming that mainframe operation, such as our cybersecurity of the next decade or so? Is that too large of a question at this point, or should we come back to it?
So let me try to answer it briefly,
Okay.
because yes, that could be a whole thing. What I'd recommend is during the Hot Chips conference, right, where we introduce the next generation processor, the Telum 2, we actually announced the Spire AI accelerator.
Okay.
So coming in the near future, there will be an AI accelerator card that you could plug into your mainframe to leverage a lot of the existing technologies. Right now, here's the secret: is a lot of the AI technologies today are only available in the cloud. Right, very few people have the cost, or the money, the power infrastructure, because these are very power hungry kind of technologies. Yep. AI in general. To do it on-prem, so a lot of them are cloud. Well, I've said it multiple times, I'll say it again. This is the world's most important data. It's very sensitive, very personal, right? Customers, our customers, Z customers, do not want to put their data into cloud locations for AI training models and not understand who else has access to those models using their data. Okay. Their data is proprietary, so they rather do it on-prem. We are going to give you an on-prem Z solution in the near future. We already give you an on-prem solution with the AIU in the Telum processor, and it's an enhanced in Telum 2 to do real-time data inferencing, real-time fraud detection, using AI today on Z16. It's only going to get better moving forward. So stay tuned. Great question.
I appreciate that, Oscar, and thank you, PJ.
Wow.
So this is, I have so much more to show you. I know I'm running out of time, but we're about halfway through. So hey, so this is my patch panel room. Every fiber optic cable out in the room out there actually doesn't directly connect to anything. Everything runs into this room. I have 200,000 fiber optic cables in this room, and I have about 3 people who live in this room full time. That's to keep it clean, to keep it documented. And just make sure, you know, we're constantly changing configurations. We're a test center, right? We're not a production center. So configuration changes is part of how we do our job. If I have to go chase cables under the raised floor, it'd take me days, weeks. In here, I could rapidly reconfigure and have a new completely configuration with Z's and coupled and storage in minutes, right?
Wow.
Using this patch panel. So 200,000 fiber optic connections live in this room. But I want to show you a full system, right? We talked about pieces and parts. I'm going to get to showing you kind of what a full system is here. Say hi to Larry. So as we walk through, in the last 3 generations ago, we made a big revolutionary change in the footprint of IBM Z and Linux 1. And that's what we're about to see here. So Z14 and generations before, and this is what you're actually looking at here, this M63 is a Z14, was the last Z to be in a 24-inch rack. Okay. There is nobody in the industry that uses 24-inch racks. The industry standard is a 19-inch rack. Historically, it wasn't a problem because Z was special. It always is special and it always will be special. But we were special. And it was always in a separate part of the data center, managed by a completely separate team. And that was fine. once we started offering a Linux 1 model, right, which is a model optimized for Linux execution, we were now competing against x86 platforms. So if I came to you and say, hey, I have this awesome machine, you could get rid of 2,000 x86 servers and run it on one Linux 1, the customer says, great. And then I tell you, but by the way, it doesn't fit in your where you're actually taking those out. We need a special footprint. Customer says, go away, right? This is not how data centers run. So we knew if you wanted to compete against Linux, right, x86 servers running Linux, we had to get to a same footprint and form factor. And that came the 19-inch rack. So on the right here, you're actually looking at a Z16, single frame Z16 in a 19-inch rack. So Z14 was the last high-end model. The air-cooled version, mid-range version, was actually the first 19-inch rack, but Z15 next to him, this is a Z15, was the first high-end 19-inch rack, and we've been in 19-inch rack Z. So this is kind of a nice family photo of kind of all the current generations of systems that are supported in the field. All the way on the end is Z13, Z14 here and there, 24-inch racks, and then I have a 15 and a 16. So nice little family photo of kind of the history of recent mainframes that we do it. Now, I didn't mention, but half of the mainframes that I have, of the 200 mainframes, half of them are Z16, the newest, latest, and greatest. The other half are a mix of N-1, which is Z15, N-2, which is Z14, and a little handful of N-3, which is Z13 at this point. Why do I have all those old systems? Well, two reasons. One is I need to make sure I can deliver fixes and patches, especially security vulnerability fixes on these multiple generations of machine for their entire life cycle. They're generally supported for 13 years after we ship it. Could be supported up to 20 years on an extended contract. And by the way, we have lots of systems on extended contract, and we still need to deliver fixes and patches for them. So I need systems to validate those fixes and patches. One. Two is I'm also doing continuous delivery. So I'm still delivering new firmware and hardware functionality on the current system and N-1 and N-2 systems, especially around the cryptography. Right? Security is a big part of our DNA. In order to stay current, we need to stay current in terms of the algorithms and the certifications and the qualifications. And we need to port that back because there's lots of sensitive data on these old systems as well. We want to make sure that data is kept secure in the post-quantum world. We talk about quantum safe encryptions, right? Where we believe in the next 3 to 5 years, quantum computers will have the ability to break the current 256-bit encryption. So we have authored 2 of the 3 NIST-approved post-quantum algorithms, basically algorithms of cryptography that cannot be broken by quantum computers. And we're going to be delivering those. We have the pre-ratified versions that we've already shipped on the platforms today. The post-ratified, they just got ratified about a month ago, not even. So we need to do some work to get those delivered. You're going to see those near term on our systems as well.
So PJ, what I heard is you've got a 13 out there somewhere that some bank in West Texas is still using, and they saw your post about the Z14 that's for sale. I saw you guys selling the Z14 last week, and so they're gonna have to buy that one or upgrade to at least a 15, 16 to keep up to date. Yeah. And then you guys are already planning for 5, 10, 15 years of encryption down the road. Is that what I'm hearing?
Yeah, so first, full disclosure, I'm not selling it. I saw somebody else was selling it. I reposted it. Everybody thought I was selling it, which is awesome. That's fine because that's something I definitely would do. But yeah, we are developing. We basically have not the shipped systems we've already shipped, but we have the next 3 generations of Z actually in development right now. So we're thinking. You're right. 10 to 15 years down the road and trying to figure out what are going to be the security risks 15 years from now when we ship that N+3 generation system. And then how do we build a design, an architecture, a processor that's hardened enough against it, right? So those are things we're always looking at in terms of the development of Z, right? And then what's coming next, right? The next Z Next is on the horizon. And then kind of the system after that, and even the system after that, all those systems are actively being developed right now at IBM.
Wow. Okay. Very cool.
So let me show you a big hunkin' mainframe. Okay. So from where my cursor is here, this line here, the 4 racks to the left are one system. This is A40. All 4 frames are one system. Okay. This is a max configured Z16. So what do I mean by max configured? We call this max 200. That means 200 usable customer cores. We ship it with more than 200 cores. We ship with spares. We ship with specialty processors, but there's 200 customer usable cores. What that gets you is the 4 keck drawers. I showed you the keck drawers. There's 3 in this frame, 1 in this frame. And what you can see here, it's a little hard, but this black kind of bracket here, there's actually a big cylinder behind there. That's the water reservoir. So there's real water in these systems, right? And then these black tubes run down and connect to each of the drawers. So that's the water loop. And then on the bottom of these 2 frames in the middle, there's 2 pumps that basically circulate the water through a radiator. So we air cool the radiator, it chills the water, and then we pump it back through the drawers, and that's a constant loop. So it's fully closed loop system that we circulate in the water. And then we have 12 I/O cages, right? All of this is all I/O. You can see all the spaghetti hanging out, right? And we're running different mixes of channels here. Ficon, Fiber Channel, which are the 2 main storage protocols on mainframes. We're running the Ethernet, so our OSA and Rocky. Rocky's RDMA over converged Ethernet for things like shared memory communication, and coupling technology, short range and long range, and also Z Hyperlink. So we have a special ultra low latency connection from Z to DSAK. It's actually a processor command that'll do a synchronous write from the processor directly to DSAK cache as if it was local cache to the processor. So those are kind of the most predominantly used I/O on these platforms as well. I want to swing around to the other side real quick, and then I'm going to wrap up. There is more to see. Come back for another time, but this is my Instagram wall. This is the money shot here. This is what the covers look like. And if you notice, most of my systems, none of them had doors. This guy has 4 doors. This is the Z16. Now these doors serve 3 functional purposes. They look pretty. That's not one of them, but they're a noise baffler, right? So this is a coal dial. So the doors go on the coal dial. You can see the grates here on the coal dial. So air's coming in and getting sucked in. So it's all fans right behind the door. So there's baffling in there to kind of reduce the noise. That's why it's really loud on my test floors, because I don't have covers on my systems. The other thing is the door on the backside has an integrated air filter. So air coming up, right? If it's dusty or whatever, there's other particulate materials in there. You don't want all that stuff getting sucked into the fan. So there's an air filter. And third, it's actually an EMC shield. All electronics emit a radio frequency. Government regulations don't allow you to interfere with other electronics. So we have to shield that in. And the door is actually part of that shielding system to prevent this emission from coming out of the box, right? So those are the 3 functional purposes of the doors. I'm gonna take a breath here. I'm actually going to just jump ahead because I can't do one of these talks without.
Well, you can take as long as you want, man. This is great stuff. The group's been great. They absolutely are active in this chat, man. They're all about this, PJ. Good. It's fantastic.
So this is where I beg you. I'm gonna hang out as long as you guys want, right? But I want questions. I want answers. We could see more and more hardware. It's a lot of the same stuff. But this is where I beg you, if you don't, please follow me on one or all platforms. I'm on Instagram, TikTok, but LinkedIn's my main jam. So please follow me there. I love talking about this stuff. I love sharing it. I love answering questions and just getting real jazzed about the technology. And most of all, I love breaking it. That's my job. That's what they pay me a lot of money to go do. So I'm going to stop there and say, if there's any questions, discussion, I'm here for it all day.
Yeah, man. Anybody in the group, man, y'all come on in and ask any questions to PJ at this point. So I appreciate you being here.
Hey, PJ, David Stennett.
Hey, Dave.
So I got to run and go help my daughter with some homework. But I just wanted to say before I hopped off, thanks for coming in and talking to us. Yeah, I appreciate it a lot. I learned a lot.
Awesome, David. Thank you. And appreciate you interacting me with on the social platform. So
yeah,
thank you.
I do what I can.
You as well.
Yeah, that's awesome.
So PJ,
you take as long as you want, man. I'm not trying to keep everybody capable. You make a stop time if you want, but I'm enjoying it. This is what we're about. Go ahead, please.
I'm here for everyone. So like I said, I could show you more stuff. I want to be respectful of people's time, but I'm gonna hang out too. So like I said, we want to keep it going. I'm here for questions, whether it be the technology, whether it be social media, whether it be anything. I'm pretty flexible guy. I love talking. I guess that's the problem. But talking about myself is my favorite topic. So that's, and then mainframes is second. I'm gonna be honest. So there's a lot of going on in the chat, which I haven't seen. Any questions we didn't get to in the chat?
Jeff's got one, I think, on the call, and then we'll go back into the chat as well.
Okay. Yeah.
I just want, this is a history question for you, PJ. When you first started out, now, which building lab were you in when you first started?
I was in 706.
Okay. So what was the newest and the oldest mainframe sitting on the floors at those times?
So I don't know the oldest. Z9 was the first GA that I was part of. So Z9 has a little bit of a funny history to it. So Z9, I'm not allowed to talk about code names, so please don't share. That was named T-Rex. It was first of our dinosaur branded code names, right? This was the generation. So I started 2003. Early 2000s was kind of the death of the mainframe. They're dinosaurs. They're not coming back. They're useless. So, being cheeky, we codenamed all our mainframes dinosaur names for a while. So T-Rex was like the big hunkin', like, let's prove the industry pundits wrong, and really set the kind of the posture for the development of kind of the modern mainframe. I would say it that way. Slightly biased because that's my first one, but the transition before that, I mean, I don't know what the oldest was. I remember the planter systems. You remember the planter systems? They were basically so we don't make those anymore. We had the air-cooled model, which was like a full rack, but then we had a planter model, which is actually half a rack, and it was called planter because it was in a box about the height of a table, and people would put a plant on it as a main. So they called it planter systems because you could actually put your plant on your mainframe as you're running it. So there was still a lot of that, right, going on, and we did have the CTVs, channel control test vehicles. So bus and tag, right, was a thing that we would still attach and test to. SCON was still very prevalent. These are old IO technologies on mainframes, but yeah, that was kind of my first product working on was Z9.
Okay.
So can I go, Jeff Brown? I don't mean to interrupt you. Go ahead, sir.
Well, I just to give you a reference, I know that now that it's getting darker here, that the beard is not showing up as well. But do you remember reading any history on boxes like, oh yeah, the 3083, the 4341?
Yeah, that was before my time, right? We spend a lot of time actually looking and talking about System 360, right, as kind of the grandfather of the current mainframe kind of
great grandfather.
Yeah, great grandfather, sure. But so 60 years of history. There's been a lot of systems since then. Unfortunately, I don't know all of them. And I didn't work on all of them either.
So, PJ, I want to put all of that together. Jeff, I love where you were going with that when we talk about history, talk about the historical value of what we're about to get into. Jeff, I want to take that thought and PJ's comment. PJ, for everybody on the call, what did 2003 PJ, where were you in life? How did 20-something-year-old PJ at that time? How old were you in 2003?
Yeah, I was 22, yeah.
So if everybody on the call doesn't know this, IBM has been said, as an industry, the industry has said IBM's the old dinosaurs, and obviously where you just went with that, PJ. So if IBM has always been on the way out, by the way, they're 70 years in now, right? They've been on the way out for 45 of those years. How did 21-year-old, 22-year-old PJ decide, I'm going to go into this? unbeknowingly walking into the T-Rex of era of IBM. How does that look for today's generation? How does that look for Christopher, Julius, Ari, Oscar, this group? They're not finding out, excuse me. I don't think the societal norm now is that IBM's on the way out. I don't think that at all.
Yeah, no. I mean, in our stock price in the last week is showing the industry is proving that too, which is fantastic. For me, so when I was going through school, I was aware of IBM, right? But I honestly, there was no forums, right? There was LinkedIn, but it wasn't like LinkedIn now. There wasn't ways that I was actually aware of mainframes, right? I was chasing my love for technology, and at that time it was fiber optics, right? I thought I was doing research on fiber optics in school. I thought fiber optics is going to be the next generation of connectivity. I'm going to work on something fresh, new, and exciting. IBM was hiring. I was like, I'm going to go do this. I go do it. And IBM's like, yeah, we've been doing fiber optics for 20 years. And I'm like, man, I thought I was onto something. But then that kind of opened my eyes and like all this amazing stuff that was going on. So I started in the IO. I did a little bit and I bounced around a little bit inside IBM as a co-op, which gave me kind of a good perspective of different pieces and parts of like, I worked on the power subsystem for a little bit. Then I went into this vendor connectivity place, and that's kind of where I got hired. I did the vendor test thing for 12 years, but I'm going to be perfectly honest. I didn't go in for mainframes. I went in for IBM's a big name, big company. The location was great. It was kind of stone's throw away from the college I went to. I grew up in New York City. I went to school, if you're familiar, in SUNY New Paltz. So it's like 20 minutes west of the Poughkeepsie plant. So they were recruiting, they were interested. I was interested. I love technology. And I just went in and I didn't, if I had access to knowing more, right. And this is part of what drives me is, we do a great job of talking about mainframes to people who know what mainframes are. We don't do a great job. Let me be very political in how I say this, in talking to mainframes to people who have no idea that this is the world's most important technology, right? So part of my advocacy and my mission is to make it accessible, not just in talking about the technology, but also just putting it as part of humor and entertainment and conversation. Because IBM's, I'm going to say, we're an old company. IBM's 112 years old, right? We have very strict brand. We have and for good reasons, right? It's worked for 100 years, but we take ourselves a little too seriously when it comes to like when we talk about this stuff in an official capacity.
Yeah,
I don't take myself seriously at all, right? And this is what you get, right? But you get the passion, you get the engagement. And I wish I had somebody talk to me about mainframes, right? And maybe I would have even gotten excited and more interested earlier, but I kind of fell into it chasing the technology.
So PJ, one, thank you for that story and that history of that 20 years you've got of the journey, how you ended up at the door and now how you ended up here talking to us tonight. I asked that question for who's left with this call right now, but I'm going to cut this out of this video because I want to share this 12 minutes with people. And here's why. I spoke with apprentices that I've been with for the last 3 or 4 years as they've gone through their journey from nowhere to IBM to now 2 or 3 years into their career. And one of them that really stuck with me was Lucas. Oh man, I'm going to get this wrong. Setchfeld. I can see Lucas's last name. He was in a chat. I apologize. But Lucas started on the floor just doing installations. You were talking about where their journey comes from. And everybody on this call probably has a software side of the house mindset or experience, or they've written code and they understand those. You walked us through a hardware side today on top of the fact of the software side of all the things that run through. But the hardware side is very, 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 very not seen. For even my apprentices. They would come to your IBM Z days and watch your tours, and they would, because they don't even get to work on a floor and go see it themselves. It's not like everybody, by the way, everybody knows, I think we're about 3 weeks out. When is Hug a Mainframe Day?
October 7th.
October 7th, we're getting a good plug right there. But the reason I say that is because not everybody knows about the hardware side. And one of my greatest journeys I ever heard in the apprenticeship side was someone that was in the hardware side. They were a vendor and they would go out and they would go to those floors and they would do those updates and they would do those
One, two.
additions, right? They would do those additions. But when they did those additions, they started seeing other areas, and you mentioned it in your talk a minute ago, other areas that were available to them, and they ventured out of hardware into writing the code that goes on those pieces of equipment and what have you. And so I think that was pretty interesting today. Julius, thank you. Julius says, hey, I think I want to end up doing more with hardware.
Yeah.
Most people don't even know, right?
Awesome.
They don't even get to see a Z16 or 14 or N1 or N2, whatever. They don't get to see those things because N-1, N-2, I gotta say it right. They don't get to see those because it's not like you get to go hug a mainframe every day. Go ahead, Cam.
No, just so you know, from time to time, IBM lets us come up. Well, every year they let us come out to the RTP. It's not really a data center, a lab, the RTP lab, not a data center. But they got mainframes out there. Most of the time, sometimes they don't. Most of the time they have. And I usually take my ECU students there. Now, is that Lucas that you were talking? Is that Lucas Zahn? Lucas Zahn?
No, it's like Steinfetch or Steinfetch.
Okay.
I can see it. I can see his name in my top my purview.
But the thing is, the reason I bring it up is because I might be able to finagle a trip to RTP with a bunch of high school kids from Wilmington to hug a mainframe day. What a photo op that would be.
I love
What a photo op that would be.
Yeah. Yeah, and it's famous. Hey, if you guys don't know, again, I've never seen one. I've never touched one. But I will tell you, Hug a Mainframe Day is coming up, and it is huge. People love their photo op with their Z. And the Lego, the full Lego Z16 is out there. Yeah. But here's where I wanted to go with that whole conversation. PJ, you talked about you ended up at the front door by happenstance. You knew that they were a big company. You knew they were on the cutting edge, and you walked in and found out they were 20 years plus into a space that you thought was brand new to the rest of the world. I love that. And the fact that you found your passion, your energy. Yes, it absolutely shows on your calls, on your socials, on your TikToks. Hey, if you guys don't follow him on his TikTokies, you got to get his TikTokies. They're fantastic, you guys. But here's where I'm going with this. This is where software and hardware in my brain blew up. And this is ridiculous because this is as ridiculous as it gets for someone like myself. PJ, you said a comment that we, and I say we in the proverbial we, right? The royal we, maybe don't do a good job talking about IBM mainframe to people who don't know about mainframe. I'm going to say, I'm going to disagree. I think you're right. In 2003, you're probably right. In 2024, Emma Skovgaard, David Stennett, people on the planet are talking Open Mainframe Project. I can give you a list of things that are out there that we do talk about it. And someone like myself who has no IT background, telephony is one thing, but no IT background, I don't know anything about it. I'm going to tell you the day that I was more interested in IBM mainframe than any other day I've spent in the last 4 years. PJ put a TikTok out there or a social out there explaining the 3 functions that he just went over for the front of that door. That cabinet door, I thought was just a sexy door. And if y'all don't know with the little, I just thought it was a sexy door, right, Jeff Brown? I just thought it was a sexy door. But PJ came back and explained those 3 functions to it. And the pride that he took in that, but the pride that every person I saw after that who got to put the new Z16 sticker when they peeled the old 15 off and they got their new doors and they put it on, that social period, everybody was out there proud to put a Z16 on their door because they were proud to be a part of that community. I thought that was powerful. And I went and printed up my 3D version. Let me see if I can get it over there.
Nice.
I've got my 3D version printed up that I could stick on my wall, even though I don't have a Z16, but I wanted to be a part of that experience of that, how proud y'all were to put that sticker on there and to explain that the door wasn't just sexy, it had 3 functions. That's where I came in like, all right, let's talk more about mainframe. And now I can talk about mainframe with the best of them. And so PJ, for you on the planet, for you everywhere that's out here, one, I want to thank you for your time. I want to thank you for your passion. I want to thank you for your energy, for sharing with us, a small group that has started this journey, and the men and women on this call that got to see Julie said it. He said it a little while ago. Hey, I think I might end up doing more with hardware because it was never something in their purview. PJ, you're making the world a better place in the IBM space. Thank you, sir.
Thank you, man. Thank you.
Yeah. Yeah. Eddie, final thoughts for PJ. I'm going to stop talking. I want to be respectful of his time and all of y'all's time. Is there anything left for for PJ tonight?
So this is how we do. We now, the people at PJ's level. I'm talking about Rosalind Radcliffe, who he knows, Donna Dillenberger. That level of folks, they are as engaged with this community as PJ is. They just need us to let them know they need us to come and talk to us. They are willing to come, and they don't have to do this. PJ is on IBM. He told you they pay him a lot of money. So let's don't talk about what a lot of money is. But he's on IBM's clock 24/7. He is where he thinks IBM's best interests are served 24/7. He wouldn't sleep, right? You got to rest. So because he's here, he sees this as part of his job, and he loves his job. So thank you, PJ, brother. And I've been knowing PJ for a while, and I don't think we've ever physically met. One day our paths are gonna cross the chair or something. They're gonna cross the chair or Poughkeepsie. Look, I damn near lived at Marist College for better than 15 years, and I was up there 2 or 3 times a year. So our paths are gonna cross. Our paths are gonna cross, definitely.
Nice. Yeah, absolutely. So they don't send me to Share because Share's a software conference and I'm the hardware.
Exactly.
We'll change it. I'm gonna get there. I have line of sight to Tech Exchange this year. I'm just working out some travel funding there. So hopefully I'm at Tech Exchange.
Oh, wait a minute. You gonna be at Tech Exchange?
I'm almost there. I'm almost there. So if you're there, come find me. Come sign up for my talks. Talks.
And we might get cable there. I mean, we got the bread. We might get cable there. We got a company on the hook. I won't say on the hook because they need to be listening. We've got a company engaged that are willing to finance our travel. So nice. Cable may be, but Jeff is definitely coming. I'm probably coming, and cable may come. So that will be a big deal. That'd be a very big deal. It's in Vegas. Oh, Vegas is not
Vegas, baby. Vegas, baby.
Listen, I'm gonna have to sign an NDA when we go there. I gotta make sure. I gotta make sure I stay within the box. I gotta stay within the box.
But the cable, we got some loot there. We have left. So we if you want to go, I don't know what your schedule is like, but if you want to go, it's only a few bucks, brother, and you can go for free. Well,
I appreciate it. I appreciate it. Hey, Cam, I'm always up for it. I traveled a lot. Yeah, I traveled a lot with my last entity, Cam. I traveled a lot with my last entity. I had an opportunity to go see both clients, apprentices, graduations. Me and Paul Newton have shared the floor many, many a times. Meredith Stoll and the rest of the IBM team that we partnered with have been fantastic as a entity to share the stage with. PJ, one day I look forward to high-fiving you in person.
Absolutely.
And that's awesome. To everybody on the call, thank you for being here. PJ, for your time this evening, thank you for that. If you haven't had dinner yet, go get some dinner and go see the family and kids. To everybody tonight, thank you. I'm going to have the link. One last message just for the group. We are switching from our Slack platform to our new platform tomorrow. So if you see that one disappear, don't be alarmed. We will have a new platform sent directly to your inbox, and we'll get everybody back into the chat community as we switch over to everything that we're going to. PJ, it's been great. I do. I love seeing that every time. I've seen it once virtually, like as a recording, but seeing it in person with your energy and the questions from the group, it's been fantastic. PJ, is there anything you need from me or from us before we let you go, sir?
No, you know where to all find me. I'm available. I love talking about this stuff. If I don't respond immediately, I do apologize. I do get busy, but I love talking about it. I love helping. If you're interested in participating in Mainframe Mondays, Push to Prod Fridays. I just started a Mainframe motivational hashtag. It's all about the community, right? And the more people that contribute and share and have fun and joke and comment and engage, that's what I do. And I love that. And I'm here to help if you want ideas or just talk. Find me on LinkedIn, Instagram, message me. I'm available. So thank you for having me. Appreciate it, Cable. Thank you for all your time. Everybody who hung out extra 20 minutes. Thank you. Thank you all.
PJ was great, and
PJ.
thank you, sir. Everybody enjoy your evening, enjoy your afternoon if you're wherever you are, the East and West Coast. But yeah, good times. And again, PJ, we'll see you out there on LinkedIn, man.
Take care.
Thanks, everybody.
Thank you much. Have a good one.
Thanks, PJ.